when people first realize that that's the general way of solving system of any equations, they also realize that in the course of this solution, the XYZ, the actual letters, XYZ, they didn't play any substantial role in the solution. We just were copying them from row to row. And so a little bit of improvement can come in terms of the amount of things you write if you start doing the operations on the coefficients alone without any XYZ next to them. This is something which is called the extracting the augmented matrix procedure. So what you do, let me just go back to my original system, using my original system. What you do, because if you just analyze how we reduced my system to the triangular shape, you have to realize that actually the XYZ didn't play any role. So what we can do, actually we can combine all the coefficients, and here will be the coefficients. Look at this, that's the coefficients which are in my first equation on the left hand side, and here's the coefficient or the number on the right hand side. Here's the coefficients on the left hand side in the second equation, and the 4 is the right hand side in the second equation. Here's the coefficients of the last one. What people realize is that rather than doing things on system of linear equations, we can do things on the coefficients themselves without copying the XYZ all the time. It will be a little bit of improvement in terms of the times and everything and the other things. It will be quite substantial improvement. I mean, originally, of course, when they decided to do this sort of thing, they were just only bothered with the, how much ink they waste on writing things. It was very, simple improvement. But later on, when they just start calling these things matrices, and in fact, this is called the augmented matrix of these, which is associated with the original system of linear equations, they realize that doing things with these blocks of numbers, or something which we will call matrices, doing things from this angle not only makes things shorter in terms of writing, but also opens many other possibilities of seeing things. But for now, all you have to remember that rather than doing things on system of linear equations like this, we will be doing things on coefficients, and I will combine these coefficients into these blocks of numbers, which we will call matrices in general, if this matrix has a connection with the system of linear equations. So you have a bar here, you have the right-hand side coefficients, you have a left-hand side coefficients, then this matrix is called augmented matrix of the system involved. Of course, my connection with the system is encoded here, that the first column here corresponds to the unknown x, second column here corresponds to the unknown y, the third column is the one which corresponds to the z and the equal sign. And the equal sign is the one where my bar is. So now, if you just forgive me this repeating of what we just done already, I just repeat what I've done with the system quickly with the metric, with this augmented matrix alone, without any copying of x, y, z. So if I just repeat this elementary operations, but this time I will be doing them on actual rows of this table, or I will use the term matrix now more often. It will all correspond to the system on the left-hand side. For instance, if I do the swaps of now actual rows, no longer the equations, here's the result of the swapping. My second row went into the first position. My last row went into the second position. And the other one like this. If I do these reductions now, if I multiply the first row by -2 and add it to the second one, and then I multiply the first row by -3 and I add it to the last one, the result of this will be this augmented matrix. Even in terms of how much space it takes, you see it takes less space. But trust me, there are much more improvements you could benefit from doing this in terms of of matrices than just simply saving space and the amount of things you write. Hopefully by the end of this year, well, even by the end of the semester, you will see a lot more benefit of doing things in terms of matrices rather than systems. Now, another row swap. which means I have to swap these two, because -1 preferable number rather than -3. So if I do this row swap now, here it is. And the final row reduction. And the final row reduction produces the matrix which corresponds to my triangular shaped system of linear equations. From this moment on, you can go back on this side of my slide, and that will be how typically your solution to the system of linear equations will look if the equation insists on the Gaussian elimination method, or if your personal judgment suggests that the Gaussian elimination will be the best way to do it. It will be going like this. You take a system, you convert this to the augmented matrix form, you do Gaussian elimination method, you end up with a triangular shaped matrix, or we will have a better name for this in a second, and then you take it back to the system form and do your back substitution. This is a general scheme how the Gaussian elimination method looks and the way you will be presenting this in your solutions. There are some extra points to this. I will deliver them gradually, but that's the basic scheme of things. So this one is here it is.